morning? You guys doing okay this morning?
Yeah. Listen, I have bad news. We are going to have class. Or maybe that's good news. But decided that I just didn't have another day out of it. My kids have been sick for like 5 days. My girl's still home. And I just can't be out of the office another day. So we're going to go out and have class on Friday. I'm sorry for any change in plans. If you've already made plans for that, that's okay. I understand. But I'll try to give you guys a day off another day in the future, okay? But this just isn't a real great day to have off at this point. So as we're preparing for the next exam after spring break. Okay? I apologize. I'm sorry for the making plans. I think that's it. Are there any other announcements? I think the tie day has been moved to tomorrow. No,
Today?
Oh, today's Wednesday.
16th, yeah.
Oh, yeah. Yeah, it is today. So it's at noon. It's going to be out in the courtyard area.
You got one?
Who?
You know who's going to be?
No. Are you about to tell me?
No. I know it's in the room between Dr. Lowe and Carthan.
Oh, yeah.
Even yesterday.
Right, yeah. They were right at about 30 or 35, I think. Okay? So catch that at noon. I'm not going to be here, unfortunately. But I kind of hope it's Dr. Lowe. Let's see. Let's pick up where we were doing this last time. You will have a multi-loop circuit on the test, which is after spring break. And then as part of that multi-loop circuit, you'll be able to pick up some extra credit. I don't know, 3 to 5 points if you solve it by with a matrix, solving that system of equations. We did this last semester. You'll remember, I think it's when we did the inclined plane. You'll be able to pick that up. Not many of you actually did that on the exam, but if you want to pick up a few extra points, 3 to 5 points, then you can solve the system of equations by finding the identity matrix. I want to go through that here. We're going to start with our 3 equations. These 3 equations. And if I rewrite these 3 equations, they'll look like this. I'm going to go to the next page. And I'm going to rewrite the equations such that they're in the form of I1, I2, I3. So I'm going to have minus, this is that first equation, minus 2I1 minus I2 plus 0I3 is equal to negative 10. So this is just that very first equation. I think that was the upper loop. This equation right here just solved for in terms, or set equal to solved in this way where I have I1, I2, I3, and then equal to whatever it is. So I put them in this form. Then the second equation I can put in that form as well, 0I1 minus I2 plus 0I3, and that's equal to negative 4. And then the third equation was I1 minus I2 plus I3, and this is equal to 0. All right, so those are our 3 equations. And then I can write these in matrix form in what we call an augmented matrix. So an augmented matrix is going to be this part, and then the augmented part is going to be here. And the way I'd write this in matrix form, I'd say minus 2, minus 1, 0, negative 10. 0, negative 1, 0, negative 4. 1, negative 1, positive 1, 0. Sometimes you see a dashed line come down like that. All right, so this is called an augmented matrix. What I want to do is get this matrix into a form that looks like an identity matrix. Okay, and an identity matrix looks like this. I have, I'll do it up here in the corner out of the way. An identity matrix looks like this. And then whatever numbers I have in the augment are going to be the solutions for I1. Because I have 1I1 plus 0I1 plus 0I3 equals whatever I2 here, I3 here. Whatever I have in the augment of that matrix will be the solution for I1, I2, and I3. And if you remember what we had, we solved this by substitution. At I3 was 1 amp, I2 was 4 amps, and then I1 was 3 amps. So when we reduce this augmented matrix down to our identity matrix that looks like this, the numbers in the augment should be 3, 4, and 1. Now there are some rules that you can do with matrices when you're playing around with them that allow you to change the makeup of that matrix. let's see, you can multiply a row by a number. You can switch rows. So where you have row number 1, you can put row number 2. Switch the order of the rows. And then you can also replace rows with sums or differences of other rows. I'll show you what that means. Sums are differences with other rows. Let me just show you what that means. It's easier to show you. So the first thing that I want to do, you might have a different way of doing this, but I'm going to first replace row 2. My very first step is I'm going to replace row 2. That's going to be this row right here. I'm going to replace it with row 2 times -1. And what that does is it gets the second row into the identity form. Because the identity form for the second row is going to be 0, 1, 0, but I have a -1 here. So I'm just going to switch that row 2 by replacing it with row 2 times -1. And what I'm going to get is -2, -1, 0, -10, 0, 1, 0, 4, 1, -1, 1, 0. And once you get one of the rows into that identity form, it becomes really simple to do the other rows. They sort of fall into place. And the identity matrix that you'll have will be a pretty easy one to solve. You should be able to do it in 3 or 4 steps. Because I'll just give you an easy circuit to do mathematically. Okay, so I can check back with my answer. I know that I2 should be 4 amps, so far we're doing okay. Now, the second step that I'm going to do is I'm going to replace row 1 with row 1 plus row 2. So I'm going to replace row 1 with row 1 plus row 2. And it'll look like this. I'm going to just add these 2 rows together and replace row 1. So here I will have -2 plus 0. So I'm going to have first -2, then I'll have -1 plus 1. So I'm going to have -2, 1. Then I'll have 0 plus 0, which is 0. And then I have -10 plus 4, which is -6. 0, 1, 0, 4, 1, -1, 1, 0. All right, so now I want to replace row 1 with row 1 divided by -2. Did I make a mistake? The second one.
Yeah, -2, 0, 0, -6 on the first step.
Oh, yes, 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 yes. Thank you. Sorry. That should be 0 because I've added -1 and 1. All right, so I'm almost here in the identity form is here as well. I just want to divide this row now by -2, and it'll give me 1, 0, 0, and then -6 divided by -2 is going to be 3. So now I replace row 1 with row 1 divided by -2. I'm almost there. I got 1, 0, 0, 3, 0, 1, 0, 4, and then I have 1, -1, 1, 0. As you get better with this, you'll be able to make these steps and maybe even combine some of the steps. Now the next step that I'll take is I will replace row 3 with row 3 plus row 2. So I'm adding these 2 rows and replacing this row with that. So I'm going to have 0 plus 1, I'll have a 1 here, I'll have a 0 here, and I'll have a 1 here, and then I'll have a 4 here. I'm replacing this row with the sum of row 3 and row 2. So my first 2 rows are the same. 1, 0, 0, 3, 0, 1, 0, 4, and then I add up the rows 1, 0, 1, 4. Now the final step is I want to get rid of this 1. How will I get rid of that 1? What will be my final step in order to get the identity matrix?
Row 3 minus row 1.
I'm going to say row 3 minus row 1, and then that'll put this final row into identity form. So I'm going to replace row 3 with row 3 minus row 1. So I have 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 0 is 1, and 4 minus 3 is 1. And then that'll be my final solution. I'll replace row 3 with row 3 minus 1, minus row 1. All right, so I get 1, 0, 0, 3, 0, 1, 0, 4, and then I get 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 0 is 1, and 4 minus 3 is 1. So that is my solution. It tells me I1, I2, and I3. If we've done this correctly, then they should be the same solutions we got by substitution. Yeah, 3, 4, and 1. Okay, you might combine some of those steps when you actually do it on the test, but let's say 5 points. I'll give you 5 points extra credit on the test. So it'll be worth your time to learn this. In fact, some of you might have done it already. Yeah?
Do we have to explain the steps when we do it?
No, but I want you to show the steps.
Oh, well, yeah, but
Yeah.
we don't have to, like, write out.
No, you can just do it. I think you do this in linear algebra. Am I right about that? So I don't think chem majors are required to take linear. Not in linear algebra? It's a good class to take if you want a math minor. I know that chem majors, like, you're pretty close to a math minor, so you might as well just go ahead and take linear algebra. And it's a fun class. It's like working puzzles all the time. Okay? This seems like an arduous way to solve a system of equations, right? Because you can solve it by substitution, at least this system, a lot easier. But it allows you to solve huge systems of equations by computing this, because there are algorithms that are pretty simple that allow you to create these identity matrices. And so while you might not do that for a 3 by 3 matrix, you can certainly do it for 100 by 100, and then it becomes useful, or 1,000 by 1,000, or 1,000,000 equations, or 1,000,000,000 equations, or whatever you need to do. So it's a nice technique to solve for huge systems of equations. If you look online too, you can find scripts that will solve this as well, where they've computed algorithms. Let's see if I can find one right quick. I'm not seeing, this might be one. There's a whole bunch of these. No, that's not it. I'll try to look for one and show you. But it's where you just put in the coefficients of your matrix, and then you can solve that system of equations. All right. I think in the homework I show that on the multi-loop equation on how to solve the system in this way. So if you want more practice, you can look at that or come see me. All right, let's try this quick test. Which of the following equations for this circuit is correct? On this one, I've actually drawn the directions of currents, I1, I2, and I3. And you probably have a question like this on the test, but on the free response part, I won't give you the directions for the currents. Remember, you'll just have to guess what the directions of the currents are, just assign directions. Which of these circuit equations is correct? You finish this one, go on to the next one. Give you about 10 more seconds on this one. I'm going to stop at 128. 128. Okay, we're sort of all over the board here. So when you go into these questions, when you're looking at a circuit, you want to start with the first equation and then ask yourself, okay, where is this? So this 6 represents what element in this circuit? It's the 6-volt battery. It doesn't have a current attached to it. I'm just looking at the voltage from a battery, so it has to be the 6-volt battery. And then you ask yourself the question, what direction am I traveling through this circuit? Am I going in this direction, or am I going in this direction? Up or down? I have to be going down, because when I go from high to low potentials, from the big side to the little side on a battery, I have a negative drop. I have a drop in potential. So I know that I'm going in this direction. Oh, but then, notice I have a minus 8I1. Now, if they were out of order, which they won't be out of order, then you could tell that that's not correct. Because if I keep going around, this should not be negative 8I1. But since I'm going against the current, it should be positive 8I1. So this one's not correct. And actually, when I give them to you, they'll be in order as they should occur as you go through the circuit. So we can tell right away that this one's not correct. Here, 6 refers to this, and I have to be going up because it's positive. So I have 6. See, is that right? Minus 8I1 with the current, so it's negative, plus 2I2. Going against the current, so it's positive IR, so plus 2I2. And then I should have a minus 12 here, a minus 12. And then here, I'm going with the current, so it's going to be minus 4I1. So B is the right answer. Let me show you what students often get hung up on. They get hung up on, one, that I1 flows in this direction on this part of the circuit. I2 goes in this part. So any resistors, like this resistor, should have an I2 attached to it. And then finally, I3 goes in this part of the circuit. So any resistors over here, the 3 ohm resistor should have 3I3 as the potential drop. And then you have to ask yourself the question, well, is it going to be a positive or a negative change in voltage? Right? If I'm going with the current, it's negative. If I'm going against the current, it's positive for resistors. For batteries, if I'm going low to high, positive voltage, high to low, negative voltage. Here, the direction of the current is not relevant. It doesn't affect your voltage change. All right, let's try this other one. If I2 is 2.45 amps, what is the magnitude and the direction of I3? What is the magnitude and direction of I3? All right, just a few more seconds. Only you want to figure out what is the correct equation that you'll want to use, because there'll be an easy way and a hard way to get the answer. This one is an easy way. I'll stop at 130. 130. Okay, so I want to know what is the current in this branch over here. Now the loop rule is pretty powerful because it tells you that in any circuit, no matter how complicated, if I can find a loop around which I know some of the currents, then I can figure out what are the other currents. And so what you want to do in this circuit, which is actually a very simple circuit, is ask yourself, what loop allows me to determine what I3 is, and I know the other values that I need to know. Now there are 2 loops that have I3 in them. There's the loop, that's the big loop. If I was to write the equation for the big loop, that would include I3. But in order to find I3, I'd also need to know I1. And then what's the other loop that has I3 in it? Right, this one. The one on the right which has the current I2. So there are a couple ways to make these circuit problems easy, and this is one way. I'll just give you one of the currents, and I'll show you another way in a sec. So here, I want to choose the right loop. I write the equation for the right loop. I'll start here. I'll go in this direction, and my equation will be 12 minus 2I2 minus 3I3 equals to 0. And then I solve that for I3. So I3 is equal to 12 minus 2I2 divided by 3. And that's equal to, what is that equal to? Do you know?
2.37.
It is 2.37. Okay, so yeah, A is the right answer there. It's going to be 4 minus 2/3 of I2, which is 2.45, and that is 2.37 for I3. Because it comes out positive, because this value for I3 is positive, that means that this direction that we chose for I3, actually I gave it to you, but this direction is correct. If it came out negative, we would know that the direction would be the opposite of what it's drawn. All right, let's try the next one. What is the magnitude of the current I1 in this circuit? Here again, I've drawn the currents for you. They aren't necessarily the correct direction, but they're just directions that I've chosen. If you pick the right equation for this, the answer is really simple. If you pick the wrong equation, it becomes kind of complicated. All right, we'll stop at about 1:30. Just guess if you're not sure. 1:30. It's 5 more seconds. Okay, good. A is right. Again, if you know the right equation, it becomes really simple. And this is another way to make these circuits really easy for the test, just mathematically easy, is that I have a branch that doesn't have a resistor in it. If I have a loop, a part of the circuit that doesn't have a resistor, then this current doesn't come into that equation when I apply the loop rule. And so if I want to know I1, there are two loops that I could consider. I could consider the top loop, and if I wrote the equation for that, I would have both I1 and I3 in that equation, so I can't solve it unless I know what I3 is. But if I write it for this loop, then that one only has I1. And so taking this, starting here and going in this direction, I get 40 plus 40 plus 20 I1 equals 0. And so I1 equals negative 2 amps. That means, by the way, that I1 is actually going in that direction, not in the other direction. Now, that seems kind of difficult because it just completely ignores this whole thing. But the loop rule still has to hold true, that the sum of the voltages around the closed loop has to equal 0. And so you'll deal with those little tricks as you work through these circuits that will allow you to find the easy way or the not so easy way to solve these. But the potentials around this loop still have to add up equal to 0, regardless of what's going on here. All right, let's one more clicker question, and then we'll try an old test question. Which of these correctly describe the circuit? So another one of these equations. Which one of these equations is correct? Doing a little bit better on this. We'll stop in about 10 seconds at 110. 110. Just guess if you're not sure. All right, good. A is the right answer. You want to go through each equation. Notice that A, it starts with minus 80I3. That means I'm going to be here going with the current. Minus 1I3. Minus 30 because I'm going from big to little, from high to low. And then I have minus 20I2. So going with the current, so it's negative when you go across a resistor. And then minus 40 because I'm going from high to low. I'm actually losing energy across that battery. So A is the right answer. Notice the other options, like for example, this junction rule, I1 plus I2 equals I3. How should the junction rule be written here? Well, my outgoing currents include I1 and I3, and my incoming currents are I2. So that I2 should equal I1 plus I3. And notice that's not what it says, so that's not correct. And then if we look at these other two, there are various problems with those. The signs are wrong on these last two equations. You'll definitely have one or two multiple choice questions on this, and I'll be looking on your free response too that you get your equations written correctly. In fact, when you have that multi-loop circuit on your test after spring break, if you get those equations correct, that'll be the bulk of the credit. Solving the system of equations will be less credit, 5, 6, 7 points out of a 20-point question. Let's try one of those. This will be something like what you have in your test. On this next one, I'm actually going to make it a little simpler for you. I'm going to remove, I want you to work it, imagining that this 8 ohm resistor just isn't there. And that makes it quite a bit simpler to solve this. So I want you to label the currents, calculate each current, and give its magnitude and direction. And if you want to later, we're not going to do the identity matrix here, but if you want to, you can do that later. So I'll give you a few minutes. Yes, Steve?
Is there a third place to start?
Now, your first step is to label your currents, and then give the directions of the currents. And then you want to write a system of 3 equations, 2 loops, and the junction rule. There are 3 possible loops you can write the equations for, but I would do 2 loops and the junction rule. First step is just label those currents. I'm going to give you about 5 minutes to work through this, okay? And then I'll jump in. 8 or 5. Be right back. just a couple minutes, though. If you solved it by substitution, try solving it by that Gaussian elimination with the matrices. Okay, so let me show you how I would solve this. And yours might be different because you might have chosen your directions for your currents differently. But let's say I'm going to take this to be I1. I'm going to say that I1 goes in this direction. I'm not really putting much thought into it. I'm just saying that's I1. I'll call this I2. And I'll have it go in that direction. And then I3, I'll say is over here. I don't know. Let's make it go that direction. So I have I1 over here, I2, and then I have I3. And then I pick two loops that I want to look at, and I use the junction rule. I'll write the junction rule first. I'll just take this junction up here. I1 is going in. That's equal to I2 and I3, which are going out. And again, yours might look a little different because you chose different currents or different directions, but you should still arrive at the same answer. And then I go through the circuit. So let's say I start right here and I go in this direction. So here I get minus 3I1 plus 12 minus 2I1. Minus, and then I'm going to come down here in this direction. And so I get minus 6. That's equal to 0. And then let's say I take, I don't know, the big loop. And so I'd have minus 3I1 plus 12 minus 2I1 minus 4I3 equals to 0. Oh, actually, no, I don't want to do that loop. Because look, I have a much easier way to approach this. Sorry. Because you recognize that I have a part down the middle that's missing a resistor, right? And so when I write this function, or this equation, notice that I only have I1 in it. So when I solve this, I'm going to get a value for I1. So if I do, in a similar way, this part of the circuit, then I'll get another equation that only has I3 in it. So let's say I'm going to go in this direction, and I'm going to have plus 4I3 minus 6 equals to 0. So those are my equations. If I was going to write them out in my matrix form, I would have 1, negative 1, negative 1, 0. Then I would have negative 5, 0, 0, negative 6. And then I would have 0, 0, 4, 6. So if I was writing it in an augmented form, it would look like that. But I'm just going to solve this by substitution really quickly. I can solve this equation and say I3 is equal to 6/4. That's equal to what? 3 halves or 1.5 amps. Notice that it comes out positive, so the direction that I chose is correct. So I'll list that as down. Then I can also solve for I1. I get minus 5I1 equals to minus 6. So I1 is equal to 6/5 or 1.2 amps. And then also notice that it's positive, so I1 I chose to be up. It's still going to be up. Or you might say that it's clockwise, however you want to say. And then I can put both of those values into my junction rule to find I2. So I2 is going to equal to I1 minus I3. So it's going to be 1.2 minus 1.5. That's equal to negative 0.3 amps. Since I chose it to be I2 down, it comes out negative. It's going to be 0.3 amps upwards. Now, something that's very important you might want to make a little note on the side, is that if I had found I1 or I3 to be negative, then when I plug them in over here, I would have kept those negative signs. Let me repeat that. So if I find one of my currents to be negative while I'm solving a system of equations, I keep that negative all throughout. You follow what I'm saying? Otherwise your numbers won't work out right. You keep the negatives on all your numbers on the values until the very end. And then you just use those negatives to say, gosh, I chose the direction incorrectly. See, while you were doing that, I did pull up a website. So there's a whole bunch of these. You just look for Google, like solve a system of linear equations or whatever. And here, look, I can put in my matrix. I have 1, negative 1, negative 1, 0. That's my augment. Negative 5, 0, 0, negative 6. And then 0, 0, 4, and 6. And if we've done it correctly, we should get the values that we have. 1.2, negative 0.3, and 1.5. Yeah, Ainsley.
When you write the junction rule, like, how do you know if it's, like, I'm just confused, like, where you can plug in stuff, because I'm always on the assumption just 1, 2, 3 equals 0.
No, that's not true. It depends on the directions of your current. Let me show you. So we wrote the junction rule for up here. The junction rule says that whatever currents are going in, so I have this current is the only one that's coming in the way that I drew it, have to equal the currents going out. So here, these currents are going out. So the junction rule will differ depending on the directions that you choose.
Okay.
Like, you could have it so that I1, I2, and I3 are all coming in, and then you would have I1 plus I2 plus I3 equals to 0. But if you're consistent in the way that you write the equations and you keep those negative signs, then you'll come out to find that, well, one or more of those currents was drawn in the wrong direction. Notice that if I write the junction rule for the bottom junction, I'll write it a little bit differently, because here I have I2 and I3 coming in, and they're going to equal to I1. So it's the same as what I wrote here, but it's just flipped. Okay? So your junction rule will depend upon the direction that you keep. Alrighty, you will have a multi-loop circuit. It'll be something similar to this. It'll probably be made easier by leaving out a resistor in one of the branches. That just allows you to do the system of equations a lot more easily. And you will be able to get extra credit by solving that matrix. Alright, that should be an easy 25 points to pick up, hopefully. On the homework, there's a question that's similar. The algebra is a little more complicated because I have resistors in all the branches, but it'll be good practice for you to prepare for the exam. Alrighty? We're going to look at RC circuits. We're going to look at them in a very simple way right now. We're going to get into RC circuits in a lot more depth later when we do AC electricity. But for now, we're just going to look at RC circuits in a very simple way. In circuits with capacitors, the current varies with time. Actually, it's not just the current, it's the current, the voltage, and the charge on the capacitor varies with time. In chapter, gosh, what was that, 4 or whatever, or no, chapter 3, when we did capacitors, we were always assuming that the circuit had already reached a state of equilibrium, so that all the capacitors had been fully charged. And so when we were dealing with those circuits, the capacitors were static. They didn't change. But in reality, whenever you use capacitors, you use them because, one, they can store energy for later, but also they vary with time in a very predictable way. When you're putting charges onto a capacitor, it's very predictable in how long it takes to fully charge a capacitor. And so it makes it very useful for when you have things that vary with time, like flashing lights or other circuits where you need something that varies with time. You can use a capacitor in order to make that happen. So if you consider this simple circuit, this is just an RC circuit, R for resistor, C for capacitor. After the circuit is turned on, the capacitor is charging and the current is waning. I'm going to show you these plots again, but if I were to plot, say, the charge on the capacitor versus time, it would look like this. As you turn the circuit on, you close the switch, you get more and more and more charge that deposits onto that capacitor. Now the maximum amount of charge, I'll repeat this later, but the maximum amount of charge is going to be equal to that Q equals CV, like we saw in chapter 4, or chapter 3 rather. And so this value here is going to be that maximum charge. This capacitor's charge will follow this function up to this maximum value. It's going to asymptote. It's an exponential function. Now, initially when you turn it on, the current versus time, the current is going to be equal to V over R. That's just from Ohm's law. And then as the capacitor charges more and more, you don't need as much current because you're depositing less charge onto the capacitor as time goes along. And so my function here is also going to be an exponential, but it's going to look like this. You'll need to have an understanding of those plots. I might have a free response to just ask you to graph, just sketch out the plots for the charge and the voltage and the time of a capacitor as it's charging or discharging. We'll see more of that in just a bit, but be prepared to do that. Now, as I said, when the capacitor is fully charged, the charge is C times V. That was just one of our basic rules for capacitors. And as it is charging, the charge is dependent. It's an exponential, and it looks like this. Q is equal to Q, which is this maximum charge, times 1 minus e to the minus t over RC. And this function, as I said, looks like this. It's an exponential function. It looks like that. Make sure that you know how to do this in your calculator, because you'll probably have a problem where I just ask you, what is the charge on a capacitor at a particular time? And so that exponential number is E on your, not the E button, but the E button on your calculator. It's usually either a second to your natural log. So there's a homework problem. Just make sure that you can do that. We'll work on it in class. In a similar way, our current, which wanes with time, is governed by this function, V over R. It's also an exponential, but it's a decreasing exponential, e to the minus t over RC. So current over time looks like this. Alrighty, I have these graphs here as well. Here's our current over time. Remember, the maximum current here is V over R. The maximum charge is C times V. Yeah, Brandon? Sure. Yeah, so this is our exponential function for I. It's a decreasing exponential function. And we'll talk about what this RC means. Got it okay? Yeah.
So this would be like inside of like a rechargeable battery?
No. No. Inside of a recharge? No, no capacitors or rechargeable batteries as far as I know. Why do you ask?
I'm just wondering.
No, in a rechargeable battery works in the sense that you send a voltage backwards through the battery. Did I show you all that video with the guy that was using capacitors for his car battery? Did I show it to you? No. Okay, maybe I'll show it. Brandon?
They actually make standard size like AAA, AA capacitor batteries now.
Oh, really?
They've recently increased their capacity where they hold the same amount of milliamps per hour, and you can charge them in 30 seconds or so.
Mm-hmm.
So you can recharge like a flashlight or a remote battery almost instantaneously. So they do exist now.
Yeah, let me show you a video, because like with capacitors, you can use them to store energy. And there's this guy on the internet, on YouTube, and he has replaced his lead battery, his lead acid battery in his car, with a set of capacitors. And Brandon's right that it takes a long time to charge a battery, because what you're doing is you're converting electrical energy into chemical energy. But to charge a capacitor, all you're doing is you're just directly storing charges on these metal plates inside the capacitors. There are some problems with using them, like to start your car, but let me pull up that video. It was actually pretty interesting. Yeah, that is something that you can do. And you wouldn't want, he had problems because as time goes on, those capacitors will slowly lose charge. They'll just lose charge like to the surrounding area. And so they won't hold a voltage like a lead acid battery will for many weeks. Or if you leave a battery for too long, of course, it'll lose its charge as well. But a nice use of capacitors to store energy for later use. All right. So that was charging a capacitor, and then after you charge it, you can remove the battery in some way through a switch or whatever, and then you can discharge the capacitor. In a discharging circuit, a very simple one would look like this. This is an RC circuit, but it's discharging. And then the current, the voltage, and the charge will all decrease with time with an exponential function. So, you know, we're looking at two different exponential functions. We're looking at the 1 minus e to the minus t over RC. That's an increasing exponential function. And then the e to the minus t over RC. And that's what we're looking at here. So our Q is going to be Q times e to the minus t over RC. I is going to be I naught. That's our initial or our maximum current, e to the minus t over RC. And then V is going to be our initial voltage, the voltage that we charged the capacitor with, times e to the minus t over RC. In all these cases, I think I have this on the next page. Yeah, but in all these cases, the function looks like this, where I have Q, I, or V, and then here I have time. Now remember, here my Q is equal to CV, my I naught is equal to V over R, and then this is just the voltage of the battery, of the charging battery. All right, so if I have Q equals CV, if I charge a capacitor, say with 12 volts, then I'm going to have a certain amount of charge. When I take away that battery, then I'll have 12 volts across that capacitor because it has a certain charge. And one more thing, the time constant, then we'll wrap it up for the day. The time for charging or discharging the capacitor is given by the time constant. We call this tau, and it has a value equal to RC. So in that exponential function, when I have e to the minus t over RC, this RC is our time constant. It's not the time to charge or discharge, but it characterizes that exponential function. The units are in seconds. Usually you'll have R in, say, mega ohms, and C will be in microfarads. And so notice that if you multiply mega times microfarads, that these cancel out. Mega is 10 to the 6, micro is 10 to the minus 6. So often when you have a capacitor or an RC circuit, then it will discharge at a rate on the order of seconds. And then finally, after 10 tau, after 10 time constants, we consider that that capacitor is either fully charged or discharged. So for example, this time would be 10 time constants. We'll work a problem next time where we actually find the charge and the time constant for our charging or discharging capacitor. Nothing's really complicated, it's just how to use the equations. Have a great day, okay? Again, I will see you on Friday, and I'm sorry for the change of plans, but I'll try to make it up to you at a later date.